So we can use the second derivative to help us find similar things, but because it's the second derivative, it's teaching us about a different aspect of the curve. And what it's telling us about the second derivative is concavity. All right, and essentially what concavity is the bend of the curve. So if something's concave down, it's sort of bent this way. And when it's concave up, it's bent the other way. And what happens is there is a point somewhere, and I've circled it here and I'll circle it again, that is called an inflection point. All right, and you'll see it spelled like this or like this, all right, depending on where you look. But it's an inflection point, okay? And I generally spell it like this, but I've seen it like that in textbooks, so just if you're wondering. So when you take the second derivative and set it equal to 0, it's going to tell you where the inflection point happens. So we can say the inflection point happens when the second derivative is equal to 0, or it's undefined. And again, we'll talk about undefined when we get to stuff that's rational, so derivatives that have denominators, because that's only the time generally, that and radical functions. But it's times when things like taking the square root of -1 or a negative number in general, or dividing by 0 is a problem. Right now, because we're doing polynomial functions at the beginning, it's not a problem. We don't have to worry about it. But we're going to do the same thing we did the first derivative with the second derivative. So it's not any different in terms of the procedure. It just tells you different information. So you take the second derivative, which is 12x minus 6. We found that earlier. We set it equal to 0, and we solve it, so we get 1/2. We put 1/2 on our number line, and then we pick a number less than 1/2. So if we pick, let's say 0, because it's less than 1/2, we plug that into the second derivative, okay? So f double prime of 0 is going to be 12 times 0 minus 6, and that gives me minus 6. So that's where I'm getting the negative from. And if you pick something bigger, let's say x equals 1, you don't have to show this, but just so you can kind of see what I'm doing, 12 times 1 minus 6 gives you 6, so it's positive. Okay, so if you're just kind of wondering where did you come up with that negative and positive, that's where I'm coming up with it. I'm plugging a number in less than 1/2, and it came up as negative, and greater than 1/2, and it came up as positive. What that tells me is, because there's a sign change, there's an inflection point, okay? So the inflection point is 1/2 and whatever the y value is. And again, every time you're looking for a y value, you go back to the original function. So I go back to 2x cubed plus 3x squared, minus 2x plus 1. And I plug in 1/2, and it gave me negative 1/2. So there's an inflection point at negative 1/2. And then, just like with the increasing and decreasing, we say, okay, what is it telling us? What's the positive telling us, and what's the negative telling us? And what it's telling us is where the function is concave up and concave down. Okay, so it's concave up after 1/2, so from 1/2 to infinity, and it's concave down from negative infinity up to 1/2. All right. So what we do is then we can compile that information, and we can actually draw the function. Okay, and I'm going to erase the actual function. I'm going to try to, so I can show you where it's coming from. But what we're going to do first, in order to draw the function, is we're going to plot the points that we found. So we found an inflection point, we found a maximum point, and we found a minimum point. So we're going to be able to plot those. Okay, so we jump back here. First, we found 2 points, negative 0.26 and 1.28. So negative 0.26 and 1.28 is sort of here-ish. Okay, and that's our maximum. Then, whoops, missed the slide here. Go back to that slide. Then we found our minimum was at 1.26 and negative 2.28. So we'll plot that again. Goes somewhere between 1 and 2, obviously, but you try to, that's 1.5, so it's kind of here-ish. There's our minimum. And then we kind of go down all the way to negative 2.28. So you kind of try to line it up. That point there was just for my reference, so we'll get rid of it. And then we have an inflection point at 1/2 and negative 1/2. So we'll put that, here's 1/2, here's negative 1/2. There's my inflection point. That's all the information I have in terms of points, although if you go back, you can get the y-intercept, because the y-intercept is just when x is 0, right? So it's just 0 and 1. That's our x-intercept or y-intercept, so we can plot that as well. And then we can kind of get an idea of connecting the dots from here, but we know that's a maximum, we know that's a minimum. So before that point, it's increasing up to that point, that's our maximum, and it's concave down. It stays concave down until it gets to here, then it switches to concave up. And we bend, and then it goes up from there. And this is a little hard to draw with this pen, but not bad. So it's concave down to here. That shouldn't be, there's no weird bend there. It just should be a normal line. And then it goes to concave up after that. But it gives us a picture. Now, we don't know what these x-intercepts are because we didn't try to find them. And we don't need to find them in terms of getting a sketch. We need to find them, and it would enhance our sketch if we wanted an exact replica of the function. Okay, but to find them, you have to actually have a graphing software that solves for you or something like that. You can use your TI Inspire if you want to and actually solve for the roots, and it will tell you what they are. But we're not going to bother with the x-intercepts because they're difficult to find. Okay, and so there's lots of different examples to do, and we're going to do more of them. But I think I'll just leave it there in terms of the concept. So essentially, just to sort of summarize so you know what we're supposed to do with curve sketching, you're essentially finding the derivative and the second derivative. You're taking the first derivative, setting it equal to 0, and figuring out where it's undefined. Once you have those numbers, so where the x values that make it 0 and the x values that make it undefined, you take those numbers and you put them on a number line, and that gives you an idea of whether there's max or mins. You find the y values of the max and mins, and then you have your points, and you also find the intervals of increasing and decreasing. Okay, and then in the second derivative, you do the same thing, but the second derivative gives you the inflection points and the points of concavity. Okay, so as a summary, let's just sort of type in or write in what we're saying. So the first step, you find f prime of x, and then you take f prime of x and set it equal to 0 and undefined and solve. Okay, you solve that. Then you put those numbers on a number line, and those values are called critical numbers. If you see that terminology. And then you use the number line to determine max mins. So you determine which ones are maximums and minimums based on whether it's positive before or negative afterwards, or positive afterwards and negative before. So you find your max mins, and then you get the, and well, I guess we'll say here the increase and decrease, because you get both of those pieces of information from the number line, and then you find the y values for your max mins. Okay. Now it is possible that the derivative is 0, but it doesn't change. So if it's flat but doesn't change, what it means is you have a sort of situation like this where it flattens out for a second and keeps going up. So it is possible to have a number line reflect that the derivative is 0 at that point, but it's not changing sign. That just means it's not a max or a min. It's still a critical point, it's called. So once you've done all of that information, then you do the same thing for the second derivative. So you find f prime of x, you set f prime of x, or sorry, f double prime of x equal to 0. You then solve that, 0 and undefined, and create a number line. And then you use the number line in this case to find inflection points. And concavity, so concave up and down. okay? And then you find the y values for your inflection points. And every time you try to find a y value, you go back to the original function. So we find the y values for the inflection points, and then the final step is to graph. And you're done. So that's the whole thing. All right. So we'll go through more in class, but that's the information you need.